In this section, we are going to talk about another data structure known as a binary search tree. In order to get an understanding of what a binary search tree is, a BST, we need to understand that it has three properties. The first property is the left subtree of a node contains only nodes with lesser values than the node's key. The second property is very similar, except with it being the left subtree, it is going to be the right subtree, and instead of it being lesser values, it is going to be greater values. And then the third property is that the left and right subtree must also be a binary search tree. So some additional terminologies that we need to understand is a root node. It is the top level node. And then we have a leaf, which is a node with 0 children. So if we did a mock tree real quick, this would be our root node. This would be our left leaf, our right leaf. Now we have another left leaf. This is no longer a leaf because now we have children here. So this is now a subtree. And this is a leaf, leaf, and this is still a leaf. So now let's look at some values and see how we can insert them. Because when you want to insert these values, there's a certain way that we need to think about it in order to ensure that our order is done the correct way. So what we want to do is we want to insert the values 8, 3, 10, 1, 6, 14, 4, 7, and 13. So let's bring this down. So the first value we want to insert is 8. So 8 is our root node. And when we insert values, we always start at the root node and then traverse accordingly. So now we're going to insert the value 3. So with 8 being our root node, 3 is less than 8. That means we go to the left and we add our 3. Similar with 10. 10 is greater than 8, so we will add it to the right. So now 3 and 10 are leaf nodes since they have 0 children. So now we go with 1. 1 is less than 8, so go to the left. 1 is less than 3, so go to the left again. Now we have 6. 6 is less than 8. 3 is less than 6, so 6 is greater than 3, so now we have 6 here. 14. 14 is greater than 8. 14 is greater than 10. 4 is less than 8. 4 is greater than 3. 4 is less than 6. 7. 7 is less than 8. 7 is greater than 3. 7 is greater than 6. And finally, 13. 13 is greater than 8, which is greater than 10, which is less than 14. So this is what our final tree would look like. So in here we have a leaf, 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 and leaf, and then all of these. So 3's subtree is 1 and 6. 6 is a subtree here. We have our subtrees here. So this is what it looks like when you try to insert values into a binary search tree. So overall, the concept is pretty simple to understand. So now that we have a good understanding of what a binary search tree is, we can begin implementing one. And we will begin implementing our binary search tree in the next lecture. In this lecture, we are going to begin implementing in our binary search tree. So the first thing that we need to do is create a struct called binary search tree, and we'll make it of type T. And something that we're going to do in this data structure is we're going to make sure that our T type implements the ord trait, which is short for ordering, because ordering is important in a binary search tree. And we'll see where it comes into play in some later lectures. So some of the fields that we're going to have are our value, and then we're going to have our left node and our right node. So our value is going to be of type option T, and then our left and right node are actually going to be the same type since they are both nodes, and they're going to be option box binary search tree of type T. So we can now copy this and paste it down for the right side. So we use an option because our value, our node, can either be none or some. And then we use a box. That way we have a definable and representable type or size on the heap. So if we look at what happens when we remove a box and then we run cargo build, we see that the recursive type has an infinite size, and the compiler is actually telling us that, hey, we need to insert some indirection so that we can make the binary search tree struct representable, and it has a couple of recommendations for us. So I went with box. That way we are represented easily and very well on the heap. So now that we have our struct set up, and also just in case you were wondering, for section 23 I ran cargo new lib section 23. That way we have a new library for us to work in, because we are going to do our test cases again. So again, now that we have our struct defined, we can begin implementing in some methods on it. But before we do that, I want to implement in the default trait for our binary search tree. And default is going to be our default behavior when we call our binary search tree. So say we call our binary search tree but we don't provide a method with it. It's going to default to the what we define here inside of our default method, which in this case we are going to call our new method. So with us calling our new method, we know that we need to call or create a new method in our actual implementation block for our binary search tree. So we can do that right now. So we'll say pub effin new, and with it being a new binary search tree, we know that we want to return a binary search tree. And when we create a new binary search tree, our new is actually going to create our root node for us. So when we return this struct of our binary search tree, this is going to be our root node. And we just give the default values of none for everything. It's an empty root node, but when we begin inserting in values, we no longer will have an empty root node. So now we're going to begin inserting in values. So we'll create a public method called insert, and since we are changing the values inside of our BST, we need to make it a mutable reference to ourself, and we want to pass in value of type T. So the first check that we're going to do is we want to say if the self.value dot is none, then that's where we want to insert our value for our insert method. So if the node is none, then we want to insert some value there. Otherwise, we need to do a little bit more work. So we want to match on our self.value, and if our value is none, then we don't have anything to do. Otherwise, we have some work to do. And remember, we need to account for, are we traversing the tree left or right, or are we going left, right, left, left, or left, right, right, left, whatever it may be. So we have to have some logic in here to make sure we know where our value is correctly supposed to go. And if you remember in the previous lecture, it looked like some recursive calls were going in when we were calling when we were inserting values, because we always started at the root node and then we worked our way down to see kind of where we were going. So we'll take that approach, and we are actually going to do some recursiveness inside of this method by calling our insert method from within our insert method. So in here we will say let target node equals if our value is less than our key, and we want to dereference our key, that way we can get the actual value inside of it. Then if we are less than, we want to make it our left node. Otherwise, we want to make it our right node, because here we are less than, but here this means we are greater than. Okay, so now that we got that situated, now we need to match on our target node, now that we have figured out what our target node is going to be. And so we want to say sum, and then if we have a ref mutable node, then what we want to do here is we want to call our insert method again on our value. And if we are none, then we want to say let mute node equals a new binary search tree. So we want to create a new subtree, and we want to insert our value, and so we're calling our insert again. And now we want to set our target node is equal to sum box new node. And we want to close this. Let's run a cargo format to make sure that we are looking good. Alright, so now we are set up. So let's go over this again. So again, if our self.value is none, then we want to set our value to some value. Now we want to match on our value, and if it's none, we have nothing to do. Otherwise, we need to figure out if we're going to go to the left or to the right with our target node. And then on our target node, so we now know that we went left or right. So now if we know we went left or right, we're going to match on that value, and then we're going to insert again. So insert will go back up here, and it's going to say, are we going left or are we going right? And then assuming that there is not another node connected to it, Well, now we can create our node, call insert again, and we know that it will go either to the left or to the right. So now that we have our insert method set up, let's start fleshing out some of our test cases, because we know that we definitely need to test this to make sure everything is working correctly. So we will say use super, that way we can bring it into our scope, and we are going to create a new tree. And I'm actually going to return a new binary search tree here, because as you're going to see, we are going to use this function in our other test cases. That way we don't spend time constantly creating new trees. We can use the same tree over and over again in our test cases for a simplified setup on our test cases. So we're going to insert a good bit of values here. That way we have a pretty well populated tree that we can work against. And so we'll insert a few more values. We'll go 27, insert, we'll go 34, and our last value we will go 15, and now we can return our tree. So notice I did not give it a test attribute above it by doing this. With this actually returning our tree here, we can't test against it. If you try to, you will get an error, but if we run our test here, let's see, and it's because I spelled left wrong, it helps, or I spelled right wrong. There we go. So now let's just make sure everything compiles happily. So we got everything compiled happily. We have created our insert method. So now in our next lecture we are going to create some additional methods as well as their test cases to make sure that our tree is being set up and working properly. So I will see you in the next lecture. In this lecture, we are going to go over implementing in our iterator for our binary search tree. So, like in previous lectures, we need to start off with creating our binary search tree iterator. And this iterator obviously needs a lifetime and then our type, where T implements the OR trait. And then our field in here is going to be a stack for us to store our values, and so we're just going to simply use a vector, and then we will need our binary search tree of type T, and we want to get rid of that. Alright, so that looks good. So now we want to create an implementation block for our binary search tree iterator. And then do the same thing where T implements the OR trait. And now we are good to go. So we will say pub fn_new so that we can create our new iterator. We will have a tree being passed in, which is going to be a reference to a binary search tree. And then what we're going to return is a binary search tree iterator of type T. So inside of our new method for our iterator, we will say let a mutable iter is a binary search tree iterator, and now we want to initialize our stack, so we'll use the vec macro and we will create it on the tree value that we pass in. So what I want to do is actually create a helper function called stack push left. So we'll do that next, and then from here we will return our iterator. So our stack push left is going to be a helper function, and it's going to contain a mutable reference to ourself. And what we're going to do is say while let sum child is equal to a reference to ourself, stack dot last dot unwrap dot left. So we want to get the left value out of our child that is being passed in, and when we do, we want to stack dot push that child. So we're pushing that left value into our stack. So what this is doing is it's getting all of the left values out of our tree, and this is going to help us when we implement in our next method, which we can do right now, and I'll be able to explain it all once it is set up. That way it's just to make sure it's super clear on what we are doing. So we're going to have our binary search tree iterator here, where t implements ord, and then inside of here we will have our type item, which is of reference to our lifetime of type t, and now we have our next method, which contains a mutable reference to ourself and returns an option So what we can do here is now say if self dot stack dot is empty, then we can return none. Otherwise, we have some values that we can work with. So we will say let node equals self dot stack dot pop dot unwrap, so get the values from inside of what we just popped, and then if node dot write dot is sum, meaning that there is a write value, then we want to self dot stack dot push our node write as a reference dot unwrap the value, and then dereference it. That way we have the actual value inside of it, and then we want to push it left. Self dot stack push left, and now we want to return our node value as a ref. So what we're doing here is in push left, stack push left, we are getting all the left values and pushing them onto our stack here. When that left value is on the stack, we're using that inside of our next value, and we're checking to see if that left value, aka that node, has some value also to the right of it. So if that node has a right value, and if it is, then we're going to push that onto our stack. So what our iterator is doing is it's getting all the values from least to greatest in our iterator. So when we iterate through our tree, we're always going to get the least greatest value first, and then the very last value that we iterate through will be our greatest value. So our tree, when we iterate through it, will always be iterated from least to greatest. And we'll be able to see that this holds true when we do our iterator test. So the last thing that we need to do now is implement in our iterator method in our binary search tree implementation block. So this is going to return a new iterator which iterates over the tree in order from least to greatest. And so it's going to be pub fn iter and self, and it's going to return the iterator trait. So impl iter where item is equal to and reference to our t value, and then very simply in here we will say we want a new binary tree iterator on our self. So this is passing in our tree right here. Alright, so all of this looks really good. So let's implement in our test cases for our iterator to see how everything is looking. And I renamed our create function here to create tree just to have it make a little bit more sense. So we have our test case, and our test is going to be called test iterator. So we have our let tree equals create tree, and now that we have our tree, we can say let mutable iterator equals tree dot iter. So now we are creating our iterator for our tree, and now we can start doing our assert equals. So remember, I said that we are going to have an iterator that goes from least to greatest in our tree at all time. So that would mean we'll go 0, 5, 7, 15, 27, 34, and 43. So that is what I'm expecting our iterator to do down here. So we'll go 0, 5, 7, 15, 27, 34, and 43. So let's put all those in. 0, 5, 7, 15, 27, 34, and 43. And then for our last one, so now that we know that our iterator is at the end, we will say our iter next, and we expect none to be returned. So everything, I believe, is good. So let's run our test and see what we have. We get an error saying no method named dref. So we need to import dref into our scope. That's a very easy fix. Thank you, compiler. So now if we run test again, we see that our test passes successfully. So what our iterator is doing, again, it is iterating the tree from with values from least to greatest. So this would mean that our tree is going to be very easy to search for values for. And searching is the next implementation we will do, and we will begin working on that in the next lecture. In this lecture, we're going to implement a few different methods. The first method we are going to implement is going to be search. So since we created our iterator, we could very easily use it to search for the value that we want to see if it is in our tree or not. But I'm going to take a different approach and not use our iterator for searching our tree. If you want, it would be good practice for you to implement another search method that does use our iterator, but you don't have to. But again, it will be good practice. So what we're going to do is we're going to create our search function method, and it's going to need our value passed in. And what we want to do is we're going to return a Boolean if it exists or not. So what we want to do is we want to use our compare and ordering in order to kind of navigate through our tree. So up here we'll bring ordering into scope. We'll say compare and ordering, And now back in our search method, we can say match and self.value, and we are going to say some key, and then inside this code block we are going to match on our key and compare it to our value. So there are three things that we can have here: equal, greater, and less. So we'll start with the easy one, which is equal. So this means that our key equals the value, therefore it is in the tree. So key equals value. So if it's in the tree, then we want to return true. Otherwise, we can have greater, and this means that our key is greater than the value, which means that we need to go to the left because we're looking for a key that is now going to be less than the value. So we will say self.left, and we will say some node, and we will say node.search, so call our search again on our value. And then if nothing comes back, then we know the value is not in the tree, so we return false. So now, and I see I have a typo here, so we will go ahead and fix that. So now we have ordering, and our last one is less than. So in here, this means our key is less than the value, and so this means we need to go to the right. So we will say self.right, and it'll be the same as above. So we'll have node.search on our value. Otherwise, if nothing comes back, then we know it's not in the tree, so we return false. And then to do our catch-all, we return false here as well to close off this match statement. So let's just make sure that the syntax is right. So let's do a cargo build, and there we go. Let's do another cargo build. Alright, so syntax is right here. So search seems to be working fine, so we'll leave it as is for now, and then we'll implement our test cases for all of the methods we're creating at the end of this lecture. So now that we have search done, let's implement a method called minimum, and minimum is going to return the smallest value in the tree. So we will say pub effin minimum, and we will need our self, and we have option with a reference to t. So in here we have our match self.left because we want the minimum, so we know that we have to go to the left, and we will say some node dot minimum because we want to get the minimum node, and we will say none if nothing is less than self dot value dot as ref. So once we get the minimum value, then nothing will be less than our self.left, so we want to return our value as a reference. So if we have a minimum, naturally we need to have a maximum, and this is going to return the maximum value in the tree. So we have self, we're going to return our option with a reference to our value, and it'll be the same thing, match and self.right, some node, and we want node dot maximum. Once we get the maximum, we will have none, and we want to return self value dot as ref. Alright, so we have minimum and maximum. Again, we will test these once we are done implementing our methods, just to ensure that they work. So the next method we want to implement is called floor. And floor is going to return the largest value in the tree smaller than the value parameter that we pass in. So we will say pub effin floor, and we know that we need our self, but this one is going to take a reference to a t-type called value, and we will say option, and we will return a reference to our value. So inside of floor, we need to do a couple of things. The first thing is we need to match on our value, and then for some key, add in a code block, and then for some key we want to match in on key.compare. So this should look kind of familiar since we just did this in our search method. And now we want to do ordering greater. So again, this means that the key is greater than the value. So we're on the right, so we're going to go to the right. Match self.right. Or no, excuse me, we want to go to the left, because in this case we want the largest value in the tree smaller than. So we want to go to the left. So now that we're going to the left, we will say sum node dot floor on the value, and then none. So if there is no value that is less than this value, then we return none. Okay, so now we have greater done. So now we want to do our less than. So we have ordering less, and so this means that the key is less than the value, which means in this case we want to go to the right because we're looking for that specific value. So we say sum node, and then inside of this code block we're going to say let val equals node.floor.value. Okay, so now we're trying to get us that value that we're looking for, and we're going to match on that value. If that value exists and is valid, well, we don't want to do anything with that value. We just want to return that value. Otherwise, if that value does not exist, then we just want to return our key. And so now all we're trying to do is exhaust all of our match statements. So this none is matching this match statement. So we will say none some key. So now we're at our last. So instead of if it's not greater than or less than, we can be equal. So now we're trying to handle that, which in that case, if it's equal, then we would just return some key. Otherwise, now if nothing works, then we just return none. And this looks pretty good. So what are we doing here again? We're matching on our value with some key. We're comparing that key to the value. If it is greater than, then we want to go to the left to try to get that value that is the greatest value but less than our value, right? So if we pass in a 6 here, then it would be great if we had a value of like 5, right? Because it's the largest value we can have in the tree smaller than 6. So that is what we're trying to do here in our floor. So if we're greater than, we go to the left. If we are less than, then we need to go to the right. Right? So if we're less than, so if we're 4, then we need to go to the right because we want to look for that 5 on the right. And then here we're trying to get that value. We want to match that value. If that value is valid and is good, then we return that value. Otherwise, we just return our key. and then we just start exhausting the rest of our match statements because Rust wants our match statements to be exhaustive. So all of this looks pretty good. Obviously we need to test it out to ensure that it looks good. So here we're going to do our test, our searching, and we're going to say let tree equals create our tree. So we want to assert if our tree.search contains a reference to 5, and then we'll do a couple more just to make sure. So we want to see if 5 exists, if 7 exists, we'll see if 15 exists, and then we'll see if 2 exists. And since we expect 2 to not exist, we expect false to be returned here, so we want to make sure that that is what we're checking for. Our next test case is going to be testing our max and min methods. So we will let tree equals create tree, and then in here we will say assert equals, and we want tree dot maximum, unwrap it, and we want a 43, and we need to dereference this guy, and then we want to do the same for minimum, so we will change this to minimum, and our minimum value will be 0. And lastly we have testing our floor. So test floor, and in here we will say let tree equals create tree, and then we will say assert equals dereference tree dot floor. We will pass in a reference to 42, unwrap the value that is returned, and if we pass in 42 in our tree, then we expect 34 to be returned. So that is why we put 34 here. So notice the value that we pass in does not have to be in the tree. So I did 42 to make sure that 34 is returned. So we don't have to see if, and we could do another floor just to verify. So we'll do floor and we'll do 30. And 30 we would expect 27 to be returned. So now if we run our test cases, we see that everything passes successfully. So it looks like all of our methods are running correctly, which is great. But now I have a little assignment for you. So there is, like maximum, minimum, there is a counterpart for ceiling, or for flooring, excuse me, and it is called seal. So we want to test floor and seal here. Test seal method. And for us to test seal method, we will say assert equals, and we will dereference our tree.seal, excuse me. And in here we will pass in 6. We will unwrap it, and if passing in 6, we expect 7 to be returned. Right? So what is seal? Sealing is going to return the smallest value in the tree greater than the value we pass in. So we're passing in 6. So if we look at our tree, what is the smallest value greater than 6? It'll be 7. So that is why we want 7 returned. So if we did another value, we'll say we'll put in 40, then we would expect 43 to be returned here. So to set this up, because I want you to take this time after this lecture to try to implement in the ceil method. So we will have our self, we will pass in our value, and we are going to return just like this. So for the assignment, I want you to implement in the ceil method, and just as a hint, it will be similar to floor with minor tweaks to it. So think about what we did for max and min and how similar they were, and try to implement in the ceil method. We will go over my solution to this assignment in the next lecture. And if you have any questions, please feel free to ask them in the Q&A section, and I will get back to you as quickly as I can. In this lecture, we are going to go over the solution to the assignment from the previous lecture. And that was to implement in the ceil method. So we are now going to go over it. So again, as I said, it was going to be very similar to what we did for floor. So we're going to have matching on our value, we're going to have some key, and with this sum key we're going to match on key and then compare the value. And so what we match on is if it is ordering less, which means that our key is less than the value, then we will match on self.right, and we will say sum node node.ceil on the value, otherwise none, return none. Alright, so now that we're done with ordering less, we do ordering greater, and then here again, now we're going to go on matching to the left, say sum node, and let val equals node.ceil on our value, and then we want to match on the value, and because we don't care what the value is, we want to just return the value, otherwise we just want to return our key. Right, so just remember, we're getting our value here, we're calling ceiling on the value, and if this is the value that we want to return, then we return our value, otherwise we just return our sum key. And now we say sum key here to be exhaustive. For this match statement, we now need to close out the exhaustion for our equals, or for our ordering, which means we can have an equal, which means that we just want to return our key. And then lastly, we want to be exhaustive on our overall match statement and return none if needed. So as I said, the ceil method is going to be very, very similar to our floor method, like very similar. What are our differences here? We have less, instead of less having all this logic, greater has the logic now. That way we get the least greatest value above our argument being passed in. So now we just need to test out our ceil method, and we have our test cases already created. So let's run cargo test, and it seems I have some syntax errors. Expected identifier found keyword, so let's go to 146 and see what I did wrong here. So I said ordering less, it would help if I added that in. Let's see if that fixes it for me. Expected here, so 164. Let's get rid of that and try it. And now it looks like we're still running successfully. Our floor and seal methods were executed correctly, so sealing is working as desired. So we pass into 6. In our tree, the greatest least value above 6 that is in our tree is 7, and then when we pass in 40, 43 is the least greatest value above 43 in our tree. So hopefully this made sense to you and you enjoyed implementing in our very own binary search tree. If you have any questions, please feel free to ask them in the Q&A section, and in our next section we will begin talking about dynamic programming.